is that the transmitted points are multiplied by some kind of n by n matrix. Okay, so now we have this, and we take the point, multiply it by a matrix here. I'm calling this script Q, where that script Q has to satisfy the following property. It times its transpose is equal to its transpose times it, which is equal to an identity. This is sometimes called an orthogonal matrix, orthonormal matrix, Q matrix, if you will. You take a matrix, its inverse is its transpose. That is an orthonormal matrix, or unitary matrix, sometimes called. And that means essentially you've rotated. And the simplest example of this in 2 dimensions is a matrix that looks like this. Cosine of some angle theta minus sine of some angle theta, sine theta, cosine theta. This matrix, if you multiply it times its transpose, you'll get a 2 by 2 identity. It's also clearly a matrix that rotates input vectors by theta degrees. And so if you do this, you don't change the probability of error. And there's a proof of that, again, in the notes, and it does depend on the noise not only being additive but being white to happen. So those are the invariances, okay, for the additive white Gaussian noise channel. So this may help you. You see a different constellation, it just looks like it's a rotated or rotated and translated version of another constellation. You already know how to analyze that first constellation. Then you know how to analyze immediately the second constellation. Which brings us to the point now we have these optimum receivers. We kind of have a good idea what that is for the additive white Gaussian noise channel, namely pick the closest point. How good is that? It's the best thing we can do, minimizes probability of error, but is that minimized probability of error 1/4? Is it 1 in a million? 1 in 10 billion? What is it? The smaller it is, of course, the more reliable our transmission system. So how do we actually compute that? And you have now, for the additive white Gaussian noise channel, the ability to compute this probability of making an error. So probability of error, probability of symbol error, sometimes called, is the probability that the message that we selected is not equal to the message that was transmitted, which could be written if we were to sum over all the messages from 0 to m minus 1. It's the probability of error given that the ICE message was transmitted times the probability that that message was indeed transmitted itself. And the probability of error given that the ith message was transmitted, we could write out more formally the probability that the decision is not equal to m sub I given that m sub I was transmitted. And this is the probability that the noise vector is such that the received vector y is an element or contained in decision region J where J is not equal to I. So that noise, that additive white Gaussian noise, is such that it caused y to fall into any of the other decision regions. Then I've made an error if message I was transmitted. I'm correct if the noise is such that I'm still in the decision region that decides message I was transmitted. Now, if I were to actually look at point I in a constellation out there in n space, and I look at message J for decision region J for any of the other messages, pick one of those, for each and every one of those, I could draw a line between xi and xj. And I could form a basis, if I will, some kind of basis function, one that would fall along that line. In the vector space, it's basically a unit vector. that goes from this point to that point. So I take that unit vector, whatever it is, and multiply its components times each of the basis functions, and I'd have a new basis function that actually is along this line. And since noise projects with variance n naught over 2, it's white additive Gaussian noise, on any basis function, or in any direction equivalently, with variance n naught over 2, what I really want to know is if the noise component on this line between I and j is greater than half the distance between these 2 points. Let's call that distance d. So the probability of this particular error event that I gets confused as j, which I'll write this way, epsilon ij, is the probability that the magnitude of that noise that's added to I here is greater than d over 2. And I write it here in case we got a negative component. We do it. Now, if it's positive component, I don't need the absolute value. And that depends on the basis function and how I defined it. That is something that we can compute. Now, it's not the probability of error yet. It's just the probability that I got confused for j. But I can actually work out what that is, because it's simply that this noise is greater than d over 2. So the probability that j got confused for I here, given that I was transmitted, is this probability of epsilon ij, which is going to be the integral from d over 2 to infinity of 1 over square root of 2 pi sigma squared e to the minus, let's say, u squared over 2 sigma squared du. And that almost is the Q function. If I make a substitution, a variable, and essentially let v equal to u over sigma, this works out to be the Q function d over 2 sigma. So if I know the distance between the 2 points, and only the distance between the 2 points, and the variance of the additive Gaussian noise, I can compute the fact that, compute the probability that message I was confused for message j. Okay, now that's just I being confused for j. Yes, sir?
Shouldn't there be a probability of I?
Sorry, I can't hear you.
Shouldn't there be a probability of I times probability of G knowing I is equal to P of P I J?
Not quite yet, because basically I'm saying that I is transmitted, okay, and now I just want to see whether it was confused for j or not. When I begin to sum things later to get the full probability of error, you're correct. So and the way to do exactly what he was asking is the union bound. And in fact, what we're going to look at is something, a very important concept in all of transmission, and we will use it again and again in EE 379A. It's a concept of the minimum distance, which is defined as the minimum over all I not equal to j in the signal constellation of the distance between the 2 points. So that's kind of like the d that we had above, but we said, what's the smallest distance? That's going to be a weak link in my system, right, the smallest distance. Because it's going to be easier for the noise to cause an error on the closest 2 points in the system. So I'm looking for that weak link. And that will be characterized by d min. And so I can then say that the probability of error, given that I is transmitted, is the probability of the union that I was transmitted and 0 was decided, the probability that I was transmitted and 1 was instead decided, all the way up the probability that I was sent and message m-1 was decided, and the only one that I don't include here is II, because that's message I was sent and message I was transmitted. That's correct. So I have all the other values. So there's m-1 terms here. Now from the union bound, if I take a probability of union events, it's less than or equal to the sum of those events. So this will be less than, in fact, these events are actually mutually exclusive. So I can actually write this as the sum, j naught equal to I, probability of epsilon ij. If I was transmitted, confused for j, okay, that's one event. It's confused for another value, k, that's another event. Those are mutually exclusive events. So I can sum those probabilities. Each of these terms can never be any worse than q of d min over 2 sigma. In other words, they're all less than that because that's the minimum distance. The smaller the distance, the higher that probability. So if I pretend that all of the points are at minimum distance, then I upper bound this, and I have m minus 1 terms. So there I have an upper bound on the probability of error. And this is the union bound. Notice this does not depend on I. So now if I go in a third step and I say summation of pi times pxi, it doesn't matter because this pulls outside the sum because it's independent. So I will have the overall probability of error is going to be less than or equal to m minus 1 times q of d min over 2 sigma. And that's the union bound for computing probabilities of error. Now, this is certainly an upper bound on probability of error. It's not necessarily always really tight. And so what we're going to do at the beginning of Thursday's lecture is we're going to investigate the nearest neighbor union bound, which is basically a way of throwing out some of the terms here in the sum, because they really contribute very little to the probability of error, and getting a very tight bound on probability of error. And we'll call it nearest neighbor union bound, and what you can guess from the name is we only have to count the points that have a common decision boundary. We don't have to count the points way over on the other side of the constellation, because once I've counted something that's got a common decision boundary with me, then I've covered. And that will reduce the m minus 1. And basically we're going to have the average number of nearest neighbors for the point over the constellation. And that will be a very tight bound on probability of error. Okay, so that's at the beginning of Thursday's lecture. Go ahead and take a look, and we'll be getting into sections 1.4, kind of 1.5 as we proceed in Thursday's lecture.